All right, there it is. Okay, so let's get started with our dive into the galactic center. So, as you all know, probably Sagittarius A star is the black hole at the center of the Milky Way galaxy. It resides in our galactic plane, in the galactic center, beyond lots of clouds and dust and stars in this really dusty and crowded environment embedded at the center of our galaxy. Sagittarius A star is 4 million solar masses, and it's lurking in the darkness, and it's hidden behind a veil of interstellar plasma in the radio, but it was unveiled by the Event Horizon Telescope in 2022, where this image was presented, and now we have added the polarization information on top of this image to show you our beautiful swirly donut. Yeah. It's beautiful, right? All right, so I have the honor to present to you our presenter team. So first of all, who am I? My name is Sara. For those who don't know me, I'm an Einstein Fellow here at the CFA on the SAO side. I'm a co-lead of this project, and I'm also the paper lead for the observational paper that came out this morning. After me, Avery Broderick from Perimeter Institute and University of Waterloo, one of our visitors, especially for this colloquium today. He is the lead of the Themis method, which is one of the two main methods for the polarization results, and he's part of the observational team. He'll be talking to you about the data properties in Sag A star and the methods that we used for the analysis. Following that will be a talk by Freek Roelofs, who's a postdoctoral fellow here at the CFA, also on the SAO side. He was the lead of the second method that was used for Sag A star results, called the M-ring method. He's part of the observational team, and he will be telling you about the validation tests that we carried out on our methods and the final results that we got. Then we move on to theory with Angelo Ricarte, who's a Harvard Black Hole Initiative fellow. He's my project co-lead, and he's also the paper coordinator for the paper lead for the theory paper that also came out this morning. Angelo will be telling you about how, what we understand about the theoretical models in Sag A star and how we model the properties of this black hole. Then following Angelo, we'll close out with Michi Baubock, who is a fellow, postdoctoral fellow at the University of Illinois Urbana-Champaign. He's also the model scoring lead of the theoretical team, and he'll be telling you all about which models actually survive all our EHT constraints and what we can learn about the black hole in that sense. And then you'll meet me again for a closeout to talk about what are the conclusions from our results and the final remarks about where we're going with the EHT. So first of all, we're 5 people presenting today, but we're part of a much bigger team. The EHT collaboration is over 300 members spread across 60 institutes, 20 countries and regions in Europe, Asia, Africa, North and South America. This is a beautiful office-style photo that was taken at the Taiwan collaboration meeting, where only 100 of us are shown, so we're actually much more than this. And of course, when we think about Sagittarius A star in the context of polarization and magnetic fields, we need to take into account the broader Milky Way context. I really love this composite that shows the mini spiral imaged by Sophia that shows polarized emission along the spiral from dust at the center of the Milky Way, and of course the gorgeous Planck collaboration image of the Milky Way dust, and you see just how amazingly polarized the galactic plane is. So it's really interesting to think about the results in the broader context of the magnetic fields in the Milky Way. So what do we know about Sag A star up until our results? So the unresolved polarization of Sag A star has actually been studied intensively over the past 2 decades. In 1999 was the first detection of circular polarization at lower radio frequencies. And in 2000, there was a tentative first detection of linear polarization, in which this lack of Faraday depolarization turned out to make the accretion estimate for Sag A star to fall by 4 orders of magnitude. So now the revised accretion rate is about 10 to the minus 8 solar masses per year, which is obviously very sub-Eddington accretion. Sagittarius A star is a really underfed black hole. Then the last 20 years, there were many detections of linear and circular polarization and rotation measure in unresolved measurements that were carried out. But linear polarization is actually not detected below 100 gigahertz. It becomes more booming at the higher frequencies, such as for the EHT. Circular polarization is always negative. It's stable in sign and increases with frequency. And the rotation measure always stays within this -5 × 10⁵ radians per meter squared number, but it is also time variable. Then proto-EHT results that were observations that were carried out in 2013 are the only observations that resolve polarization of Sgr at any wavelength up until these new results. These first observations of polarization showed strong polarization on long baselines, over 100% interferometric fractional polarization. And it's also asymmetrical, which implies that there's spatial changes in the polarization pattern along the image, but this was insufficient to actually make a polarized image of the data. These results were published in 2015 in a publication led by Michael Johnson. And so what we learned from this is that Sgr has strong polarimetric variability, and this was already pretty valuable constraints for theoretical simulations of the accretion flow in Sgr. So what have we learned from everything so far is that Sagittarius A star is an extremely underfed black hole. It's a sub-Eddington accretion. It's a radiatively inefficient accretion flow. It is time variable, also in polarization, and there's a lot of persistent evidence that the magnetic fields are steady and partially ordered near Sagittarius A star. But unlike for M87 star, which we have published a few years ago, there are almost no previous polarimetric measurements of Sgr using VLBI, so VLBI images of Sgr in polarization. And today, well, this morning, we revealed the first polarimetric images of Sgr, and I'm very excited to let the team tell you our story. So next will be Avery to talk about the EHT observations, data properties, and imaging methods.
All right. Thank you, Sara. And it's a great pleasure for me, and I imagine for everyone in the EHE, to be here today to share this exciting science with you. So let me begin by introducing the Event Horizon Telescope circa 2017. 8 stations located at 6 sites observed Sag star for 5 days in April. The 2 days that we're talking about here are April 6 and April 7. For various technical reasons, those are the 2 days that are appropriate for polarimetric imaging. 2 bands, 3.5 petabytes of data. It's literally half a ton of hard drives. So how does one express what resolution that sort of instrument buys you? I used to talk about reading the small print on dimes on the other side of the planet. In Canada, of course, I'm obligated to make a hockey reference in every presentation. You can watch the hockey game on the moon. I still remember trying to watch hockey games in normal def. That was a mystery to me. But I think maybe the best example is the size of atoms. So if you had EHT eyes and you put your thumb out, not only could you see your thumb, not only could you see your fingerprint or the little hairs on your thumb, you could see the atoms that make up your thumb. Okay, these are the highest resolution images in the history of astronomy, and now they are polarized. How do we achieve that feat? Like all interferometers, it works by combining information from stations located at very different locations on the globe. And these are related to the image on the sky by a Fourier transform. That is, if we take data from these 2 stations and combine it in the right way, we get a representation of the Fourier transform of the image on the sky evaluated at a spatial frequency set by the separation of those 2 stations. Now, of course, life is not simple. It's not always ideal. And there are a number of effects that complicate the interpretation or this relationship in practice. 2 examples would be absorption by water vapor in the atmosphere or phase delays in the troposphere. And because of this, for the past half century, radio astronomers have developed a number of data products or aggregate data quantities, things like closure phases and closure amplitudes. Closure phases are especially interesting in the annals of interferometry because they are an indicator of asymmetric source structure. They are 0 for point symmetric sources. And of course, there are multiple polarizations of light, so we can perform this sort of experiment not just with 1 polarization, but with 2. And the EHT utilizes the circular polarization basis So we have right-handed circular polarized light and left-handed circular polarized light, and you could imagine correlating or combining the right-handed signal at one telescope with the right-handed signal at the other, or the right-handed and the left-handed, and all the combinations thereof. And that produces not one quantity, but four quantities we call a coherency matrix. It's really four of these Fourier transform things, these visibilities. And those are related not to just the Stokes I image, but the full set of Stokes parameters. So I, Q and U, which encode something about the linear polarization, and Stokes V, which says something about the circular polarization. And so this is what we are looking at today. Of course, with that, you can still construct your closure phases and your closure amplitudes, but there are other polarization-dependent quantities that are more interesting for polarization study. One is this mBrev, or interferometric polarization fraction. It's really the ratio of the Fourier transform of Stokes Q and U to Stokes I. Okay, so that's kind of a strange thing to think of. It's not bounded to be 1, but it does indicate magnitude of polarization and in some sense, the direction of the plane of polarization in a scale-dependent way. And then there are these closure traces that were discovered just a few years ago that not only avoid things like the atmospheric effects I described, but also a variety of other potential degradations at each telescope. And a certain combination of these closure traces ends up being a sensitive probe of polarization in the same way closure phases were for asymmetry. Okay, it has it's I think unity when there is no polarization structure, and it is non-unity when there is. And we'll see something about that a little bit later. So here's a representation of the data on April 6 and 7 from the 2017 observing campaign. And what's being shown here is this mBrev. Each one of these ticks has a color that tells you the magnitude of mBrev and an orientation, which tells you the complex phase of mBrev. You can interpret that as some version of a polarization direction. And you can see that there's first a lot of polarization. This mBrev goes up to 2. That's allowed. Think that, just imagine that means that it's highly polarized. And you can see that there are periods of well-defined orientation. But it isn't always in the same direction. Okay, and we expect that. Sara already mentioned that Sgr is variable. This is not a surprise. We know M87 changes on a time scale of a few days. Sgr being 1,500 times less massive ought to change on time scales of minutes. We certainly see short timescale variability in the light curve, and we saw this in the total intensity. We also see this in the polarized structure without even making an image. You can look at locations in this spatial frequency plane, this Fourier conjugate plane we call the UV plane, at baselines or different sets of pairs of telescopes which sample the same spatial frequency but at different times through the night. And you can ask, are the data similar or do they materially differ at those different times of the night from those different baselines? And the answer is they differ. So we have direct evidence even in the data without looking at an image that there is polarimetric variability on timescales shorter than an hour. And this creates a challenge. Most of the methods to do image reconstruction depend upon Earth aperture synthesis. Being allowed to wait for an entire night to collect data, fill in that UV plane, and then invert that Fourier transform. But you can't do that if your source is changing on minutes. And there are two strategies that we have pursued. The first is to essentially make a poor image reconstruction many, many times through the night on short time scales, and then average those poor reconstructions to improve the fidelity of the image reconstruction. And the other is to develop a statistical model for looking at the variations in the data and fit a single average image reconstruction all at once. You can call these, averaging after fitting or averaging before fitting, or post-marginalization over the noise and pre-marginalization over the noise. Okay, so now it's just a simple business of taking that data that I showed you, inverting the Fourier transform, and constructing an image. Not so fast. That was not the only set of complications. There's also the fact that the UV plane is not fully covered. We have to fill in the spots that are empty with either assumptions or priors based on what we think the image could look like. For example, there are no intensities below 0. That's a free one. There's no polarization fractions above 1. That's another free one. And how you might fill in that information, how you might invert this Fourier transform. One makes a number of different potential assumptions. And you might worry that your ultimate image is dependent upon exactly the kinds of assumptions you made. And that's why we didn't use 1 or 2, but 4 different methods to try to reconstruct the image. And the one thing I want to drive home is the diversity amongst them. Okay, so here's a table, which I'm just going to walk through schematically with you, of the 4 different methods we looked at. They used different representations of the underlying image. Some use wavelets, some use pixels, some use models. They look at different parts of the data or different data products. Some use those closure phases and closure amplitudes and mbrev. Others use the coherency matrix in full. They make different assumptions about the calibration process during the image reconstruction. They make different choices about how to mitigate the variability. Some do the averaging before, some do the averaging after. And they produce different outputs. Some produce optimal images and then survey over assumptions that went into the underlying algorithm. And some produce a posterior with probability tagged images that give you a way for assessing how significant features might be. So in summary, we used many methods that differ in almost every possible respect, conceptually and practically. Different assumptions about the image, different data products, different variability mitigation schemes, different outputs, imaging outputs. And the hope then is wherein they would agree, we are seeing true signals on the sky and not artifacts in the analysis. Next, I'm going to allow Freek to tell you why we believe that's true and what we found.
All right. Yeah, so as Avery said, we have all these different methods to deal with the complexities in the EHT data and our challenges, which are the limited Fourier coverage, the time variability, and the sources of systematic noise in our data. So to test how well our reconstruction algorithms do at reconstructing the polarized source structure, we rely on synthetic data tests. And what we do here is we start from a ground truth source model, like here. This is a GR-MHD movie of Sagittarius A*. We simulate observations of that movie with the exact same UV coverage and noise properties as we have in our data. And then we apply our analysis algorithms to this mock data set and see what the reconstructed images look like and evaluate them with different metrics. So to do this, we use 2 models. These are both coming from the same GR-MHD model that is consistent with our constraints on total intensity for Sagittarius A* that we published in 2022. Here you can see the time average image of both models in linear polarization on the left and in circular polarization on the right. In circular polarization, you can have right or left circular polarization, or positive and negative, which is indicated with the colors. And overplotted here are the total intensity contours. When we looked at the polarization properties of this first model 1, we saw that the polarization variability is comparable to what we see in the actual Sagittarius data, but the net polarization fraction of this model was quite a bit lower, which would make imaging the polarization structure more challenging because of the lower signal to noise. So to compensate for that, we from this model we generated this second model where we rescaled the polarization to the net polarization fractions that we actually observe in Sagittarius A*. But as a consequence of that, we see that the resulting polarimetric variability in the second model is much larger than what we see in the data. So these 2 models are reasonable representations of the polarization in Sag A* in slightly different ways. So let's have a look at how our imaging methods do on these synthetic data sets from these 2 models. So here on the left we have the ground truth for model 1 and 2, and then in the different columns here we see our different imaging and modeling methods. And here looking at the linear polarization, we see that there are certainly differences between these, but they all agree on the main important features in our polarization image, which is this nice twisty linear polarization pattern. even though we had to deal with all these challenges, including the rapid variability. So this was quite encouraging for us to see. And we see here also in model 2, which has the large polarization fractions, that indeed all these models then also recover a larger polarization fraction along the ring. Looking at the circular polarization results from these methods, the picture changes a little bit. Circular polarization is a much weaker signal than linear polarization, which makes everything more challenging. So there are some more significant differences here between the different methods. But we see, especially on model 2, that some methods are doing reasonably well. For example, Themis here reconstructs the circular polarization quite faithfully, and also the M-ring geometric modeling method, which we developed here at the CFA. This restricts the allowed structure to very simple structures, but here we see it's still able to get the negative circular polarization near the total intensity maximum, and then a positive circular polarization component in the north. But overall, circular polarization is more uncertain than linear polarization. So rather than just looking at the images and comparing them by eye, we also want to do some more quantitative comparisons between our reconstructions and the ground truth. And then what we can do is we can decompose the polarized ring into Fourier modes. And you can see some examples of these modes here. We especially look at beta 1 and beta 2, where beta 1 gives us a measure of the first order asymmetry in the polarization pattern, and beta 2 is a measure for the rotational symmetry. So by having different beta 2s, you can go from, for example, here a radial to an azimuthal pattern, and the complex modes here we get this twistiness in different direction. In addition to the Fourier decomposition, we also look at the net unresolved linear polarization fractions and also circular polarization fraction, and to the average resolved polarization fraction across the image. So here you can see some comparisons of these quantities of the different methods to the ground truth, which is indicated with the horizontal bands. And we see overall the models are doing pretty well, getting the ground truth polarization structure parameters. We see for 2 of these methods we have error bars. These are Themis and M-ring. These are our posterior exploration methods, and the imaging methods do not give error bars. And we also see that the posterior methods do relatively well reconstructing these ground truth parameters. So for the interpretation of our results, we will use the posterior exploration methods, while the other 2 methods, the imaging methods, are more used as validation methods. Okay, so now that we have an idea of what our algorithms can do on the EHT data, let's have a look at what they do on the real data. So here's again the fractional linear polarization in the visibility domain that Avery showed, where we see this rich structure. We see varying MBREF along UV tracks, and also differences between UV tracks and between different days. So this is telling us Sgr really has a rich polarization structure. One other way you can really show that is using this data product, which we call the conjugate closure trace product phase. I won't go into detail about what it is, but the thing to remember is that this is calibration independent, so it doesn't depend on any of our calibration assumptions. And if we see a non-zero value of this quantity, we know that we are looking at a source that has some interesting resolved polarization structure. And as you can see here, we definitely measure non-zero values, and we also see that they differ, for example, between April 6 and 7. So this is really showing unambiguously that Sgr has an interesting and time variable polarization structure. So let's look at the images. These are the 4 average images from our different methods. You can see, again, like for the synthetic data test, there are some differences, but on the overall polarization pattern, they agree very well. They all are showing this twisty and more azimuthal linear polarization pattern for Sagittarius A star. And the image that you've seen is the average image over these 4 methods. So moving on to circular polarization. For circular polarization, a data product that we want to look at is the closure phase. This was also introduced by Avery. It's the sum of the visibility phases on a closed triangle of baselines. And in taking the sum over this closed loop, we cancel out station-based phase errors like those introduced by the atmosphere. And it turns out if you compare the closure phases between the parallel hand correlations, so between right-right and left-left, if you see a non-zero difference between those two, you know that you're looking at a source that has a non-constant fractional circular polarization. In other words, some interesting polarization structure. And we see indeed for the EHT data, this is an example for one of our baseline triangles from ALMA in Chile to the SMA in Hawaii to the LMT in Mexico. And we see that there are significant differences between these right-right and left-left closure phases. The differences are plotted here. So this is proof that indeed we have detected a circular polarization structure on scales of the event horizon for Sagittarius A star. So let's have a look at how our imaging methods do on circular polarization. And here we see that all of our imaging methods are reconstructing negative circular polarization on the right side of the ring, and our 2 posterior exploration methods are also recovering a positive circular polarization component on the opposite side of the ring. And we see an overall presence for relatively simple circular polarization structures, but our 2 imaging methods do not see this positive circular polarization component, so there's a bit more uncertainty in the circular polarization image than in the linear polarization image. So these are, again, these different image-derived quantities that we can compare between the different methods and between methods and models. I'll just highlight a few of those. One of them is this resolved linear polarization fraction in the image. And we see we get quite tight constraints from our posterior exploration methods. And we see that it's quite high. It's like 25 to 30% for a Sagittarius A star. We see that we could constrain the image resolved circular polarization fraction to within a few percent. And another interesting quantity to look at is this argument of beta 2, the rotational symmetric modes that will tell you the twistiness of this polarization pattern. And here, the fact that these are all close to 180 degrees is telling us that the polarization pattern is more azimuthal than radial. So now to tell you what this all means and how we can interpret these images and quantities, Angelo will take over.
All right, thank you. We're now transitioning to paper 8, the theoretical interpretation paper. So here are, again, our images of Sagittarius A star. Starting with these for theoretical interpretation, as you just heard, we're more confident in a consistent linear polarization pattern than for circular. And so structurally, we want to interpret the linear polarization more than the circular polarization. So what are we looking at? I'll remind everybody that the extremely low accretion rate, or Eddington ratio, of Sagittarius A star implies we have a puffy, hot accretion flow that's geometrically thick and optically thin at these wavelengths. We're pretty confident that what we're looking at is synchrotron radiation. That is the radiation coming from particles that are whirling around a magnetic field, and this is great for a number of reasons. Synchrotron is intrinsically very highly polarized, nearly 70%, in linear polarization, and it also traces the geometry of the magnetic field. Now, from previous work looking only at the total intensity data, our non-polarized images had already preferred models that were non-zero spin, relatively face-on, and strongly magnetized. Many of us were worried that we were already cornered into such a small region of parameter space that there would not be any models that would be left once we included our new constraints. The large polarization fraction with this high degree of rotational symmetry. But as you'll see, it turns out that we did better than we expected. So in terms of the large polarization fraction, as Freek mentioned, this is one of the things that we measure the most precisely. As you can see here, based on the color bar, it's actually constrained to within 24 to 28%, which is really high. It's higher than M87, which was around 10%. And this disallows a lot of tangled magnetic fields on smaller scales than what we observe. We have a lot of analytic arguments similar to this in the paper, if you want to learn more. But our bread and butter has always been these complicated fluid simulations. We start with general relativistic magnetohydrodynamics, or GRMHD, where you evolve a magnetized torus of gas in a Kerr spacetime of a given spin. And here you can see visualized both the disk in orange and jet in white here, which forms self-consistently as the gas evolves. The white ribbons in the background there are the magnetic field lines. And then there's a separate calculation to get the image, general relativistic ray tracing, or GRRT, where first you solve the null geodesic equation for the motion of light, and then do polarized radiative transfer along those geodesics. There are interesting and very useful differences between the simulation view and what we expect to see with our telescopes. In particular, this side is brighter than the other side due to Doppler beaming or Doppler boosting. And this allows us to have some constraint on the inclination of our sources. It's one of the reasons, since Sgr is so symmetric, that we tend to disfavor models that are more edge-on. But polarization can give you even more information than the total intensity, allowing you to break degeneracies and probe the magnetic field geometry. Take these two models, for example. Although they look extremely similar, they're actually simulating different plasma conditions. But even with perfect resolution, I certainly can't tell them apart by my eyes. And if one were to blur these to the resolution of the Event Horizon Telescope, it would essentially be hopeless. These two models are indistinguishable, no matter how well you can sample them in total intensity. But then, let's turn on linearly polarized glasses. Suddenly, the two models look very different. Here, the tick lengths encode the total amount of polarization, and the tick colors encode the polarization fraction. If you look at these long enough, you'll notice there's more blue on the right than on the left, which allows us to infer that this model is actually colder than the one on the left. It's just making up for this with a higher density and a higher magnetic field when it comes to the total intensity. You would have also noticed this difference in the morphology, and this also carries true in the circular polarization. Here, the red corresponds to counterclockwise circularly polarized light, blue is counterclockwise, and you'll find more blue on the right than on the left. This is related to the line of sight direction of the magnetic field, which is pointed away from us on the right and towards us on the left. Now, these are all very turbulent movies. This is all a lot clearer when you look at the time average. And you can see that if you started off with models that looked like this, it's hopeless to even go for perfect resolution. You'd be better off discriminating them with polarization. In addition, I mentioned that polarization will tell you about the magnetic field. Like with M87, we believe that we're looking at an accretion flow that is mostly face-on. And for matter that is orbiting around circularly, they will tend to drag the magnetic fields into a similarly toroidal pattern. Again, because we're looking at synchrotron radiation, the polarization that we observe is going to be 90 degrees offset from that. And so a purely toroidal field will give you a purely radial field, which will also be modified by additional plasma and GR effects as well. In the case of Sgr, we have reasons to believe that a clockwise inflow is dragging the accretion flow into this sort of spiraling pattern. which would then lead you to a polarization pattern that is oriented with the opposite-handedness. But hold on, this pattern actually is a bit different from the one that we showed you earlier. We actually think we require additional plasma effects to transform it into the observations that we've seen. Now that we have these two images, M87 and Sagittarius A star, it's important for us to compare and contrast the two. And we're finding that we have sweeping, symmetric polarization patterns in both, implying strong magnetic fields for both of these black holes, which we're wondering may now be universal. But perhaps you were worried when I said additional plasma effects, and we theorists are worried about this as well. By additional plasma effects, I mean Faraday effects. As polarization travels through a magnetized plasma, it'll get rotated by Faraday rotation, which is going to change the orientation of the polarization, here going from up and down to left and right in that cartoon example. And then there's also Faraday conversion, which exchanges linear and circular polarization. We believe that Faraday rotation is more important than Faraday conversion in the sources that we're studying. And it is actually very significant when it comes to modifying the polarization pattern. In general in astronomy, people who measure polarimetry often will like to derotate this polarized image. Because in the picture where you have an external Faraday rotator that's separate from the emission, that's somewhere in between us and the emitting source, you're safe to cancel out that effect by measuring the rotation measure, the change in the EVPA as a function of lambda squared, and then because Faraday rotation has a lambda squared dependence, you can basically get rid of it. For Sagittarius A star, we observed a rotation measure that corresponds to a 46-degree rotation, which is pretty significant. However, we're not actually sure if this really corresponds to an external screen or if this is something co-spatial with the plasma that is emitting. We have contradictory directions of evidence that are pointing us one way or the other. And so in the end, we decided to keep both options open. So one thing we think about a lot is which of these is the actual intrinsic polarization pattern that we should be comparing with the simulations. The pattern that's observed on the sky would imply a counterclockwise inflow. And in particular, the reason we don't like that as much is because there are multi-wavelength flares that are also polarized that have been implying a clockwise inflow instead. If you derotate by the rotation measure, you recover that handedness. But of course, we do this with a much more sophisticated scoring process, which Michi Baubock will now tell you all about.
Okay, yeah, so I'm going to tell you how we actually go about comparing these wonderful new observations to the model library that we have built of GRMHD simulations and determining which of those simulations are now consistent with the observations and which ones are not. So this is a picture, if this very large video will load, of just a handful of the simulations in our model library. This is not even a third of the number of simulations that we included in the whole analysis. So we've run this very large library of GRMHD simulations across a large parameter space of parameters that we're interested in. And I list the parameters, the interesting parameters, the non-nuisance parameters over here on the left, which are the black hole spin. The black hole can be spinning with a positive or a negative sign, implying a co-rotating or counter-rotating accretion flow. And then the value of that spin goes from 0 to 1 in the extremal case. We vary the observer inclination, unlike for M87, where we have a good idea of what the inclination is by looking at a large-scale jet. For Sagittarius A star, we don't have any idea what the inclination of the accretion flow is with respect to the observer. So we sample that from face-on clockwise at 0 degrees all the way to face-on counterclockwise at 180 degrees, and 90 degrees would be an edge-on view of the flow. We sample two different sort of classes of simulations which have to do with how strong and dynamically important the magnetic field is. So if you seed your simulation with a strong magnetic field, you end up in this mad state where the pressure of the magnetic field is pretty comparable to the pressure of the gas in the accretion flow. So these are sort of, the magnetic field plays a large dynamic role in the accretion of the gas. In contrast, for the sane models, we seed them with a weak magnetic field where everything is just dominated by the gas pressure. So as the plasma accretes, it just drags the magnetic field along with it, and it's dynamically weak and relatively unimportant. We can reverse the magnetic field polarity, pointing the magnetic field one way or the other in our simulations. And lastly, this electron temperature. This is sort of one of the biggest uncertainties in our models is how the electrons are actually heated, which we parameterize by this R high parameter, which essentially tells you how efficiently can electrons be heated in a weak magnetic field. So a small R high value leads to a sort of hot mid-plane disk of electrons, with most of the emission coming from the mid-plane of the accretion flow, whereas a large R high value will sort of light up the jet or the jet walls of the accretion flow. And then our constraints, as Freek already showed us a few slides ago, let me just remind you that we're comparing each of our models to these 8 constraints, which are the unresolved and resolved linear polarization fraction, and then these beta modes, which tell you about the structure of the polarization. And in particular, the one that's going to be important and tricky to interpret is the phase of beta 2, which essentially tells you the pitch angle of the polarization ticks on a ring. So we'll look at this in more detail in just a minute. And then we have 2 more circular polarization modes, the unresolved and the resolved circular polarization fraction, where given that our error bars on these are much larger than the linear polarization, these provide much weaker constraints and barely rule out any models. So since this phase of beta 2 is going to be a little trickier to interpret, let me first show you the constraints if we ask which of our models are consistent with all the rest of the constraints. So everything except this phase of beta 2. And we see there's sort of a pretty large fraction of the models that are consistent. We were worried that all of our models would be ruled out immediately, but that's not the case. And you can sort of, while of course this is a very poorly sampled parameter space, so I wouldn't trust exactly saying, inclination 70 is ruled in and inclination 80 is ruled out, for example. I think we can look at sort of overall trends in this picture. So let me walk you through. I'm going to show you several of these plots, so it's worth telling you how they work. We call these pizza plots for obvious reasons. They're pizza slices. The top row are all the sane models. The bottom row are all the mad models. As you go azimuthally along the crust of the pizza, you're viewing from face on at 10 degrees all the way to edge on at 90 degrees. The radial slices here tell you this R high parameter. So this is models where the disk is primarily emitting versus all the way out at 160 where the emission is primarily coming from the jet. And then we have 5 columns corresponding to 5 different spins. Negative spins are ones where the black hole spin direction is in the opposite direction of the angular momentum of the accretion flow, and positive spins are ones where those are aligned, going from almost extremal to 0 spin where the black hole isn't spinning at all. So looking at this, we have sort of strikingly, there's only a very few, and of course, orange fields here are models that fail one or more of the constraints, and green or blue fields are models that pass, with the different colors of blue telling you whether they pass if the accretion flow is clockwise at greater than 90 degrees, this light blue, or counterclockwise at less than 90 degrees, this dark blue. So you can see we sort of generally prefer mad models. There's only a very few select sane models that get by all of our constraints, which is, again, consistent with what we found in M87, that mad models are preferred. And we're sort of in this intermediate inclination region where we rule out all of the models at 90 degrees and all of the models at 10 degrees with a few maybe just one exception, but these models from 30 to 70 degrees seem to do reasonably well. Then let's look at beta 2. The problem with beta 2 is that it depends on this derotation of the Faraday effects that Angelo was telling you about. So I'm going to show you two versions of this plot. The first version, where we take what we observe at face value, we don't do any derotation, and we just apply our constraints. So this would be the scenario in which all of the Faraday rotation is happening very close to the black hole, where it's already naturally included in our simulations. When we do the ray tracing through our simulation box, we're seeing all of the Faraday rotation that happens in nature. In this case, what I want you to focus on is the dark blue, the prevalence of dark blue here. So more of these models at less than 90 degrees, corresponding to a counterclockwise accretion flow, are passing in this scenario, compared to when I show you the same plot, but now with derotation. So this is the scenario when all of the Faraday rotation is happening far from the black hole, where it isn't intrinsically captured in our simulations. So we derotate first before comparing. And now you see that many more of these inclination greater than 90 models are passing, corresponding to a clockwise accretion flow. Now, we can combine these, this constraint with the plot I showed you earlier. And again, I'm going to show you two versions without derotation and with derotation. And just to remind you, here's the corresponding image on the left. So without derotation, the only models that pass are these ones with counterclockwise flows at inclinations less than 90 degrees. And otherwise, the story is very much the same as what I showed you earlier. So moderate inclinations, mostly MAD models. But importantly, if we make this choice, there's no model that survives here that also is consistent with our total intensity constraints from our 2022 paper. So if we do this, we have ruled out all of the models. If, on the other hand, we derotate first, again, the picture looks very similar, moderate inclinations, mostly MAD models that pass, but now you can see that all of the models are indeed this clockwise accretion flow. And notably, this one extra model has popped up here, and this model is one that happens to also have passed all of the total intensity constraints. So this model so far is consistent with everything that we have been able to throw at it across both total intensity and polarization. I very much want to emphasize that this does not mean that this is the model that is correct, and we know this about Sgr, that it is at inclination 30 degrees and at spin plus 0.94. Our sampling of the parameter space is very sparse. There's a lot of assumptions built into this. So I think it's more useful to think of this in terms of there's a suggestion. I think we can say that MAD models are preferred. I think it's very, very preliminary to say this is the answer. So what does that model look like? The model that is consistent. So over here, I'm showing you the average images. The total intensity is the grayscale on the bottom, and the tick marks show the linear polarization. This is the full resolution version, the infinite resolution version from our simulation. And then this side shows you what it looks like when blurred to EHT-type resolutions. And the same thing for circular polarization down here at the bottom. And then on the right, I show you where the emission is coming from. So this is a map of where the photons that landed on the image plane during our ray tracing of the simulation, where those photons started off life. You can see that they mostly originate in this jet wall. So there's no emission from out here at large radii in the midplane. The emission is definitely peaked close to the midplane at small radii, and then as you go out, you're seeing essentially this jet wall, which again is because this simulation happened to be one with an R high of 160, corresponding to these hot electrons in the jet and colder electrons in the central disk. So this is it. This is our best look at what we think the properties close to Sagittarius A* could be like. And I will pass it off to Sara for some closing remarks.
Hello again. So I'll make this quick so we have time for questions. All right, so now that you're intimately familiar with our new image of Sagittarius A* and polarization, I want to take you back to this beautiful picture of our two black holes in polarization. Angelo already described that we're seeing these strong and ordered magnetic fields for both M87 and Sagittarius A star. And I want to especially point out that these two black holes come from very different environments. So M87 is, of course, 6.5 billion solar masses. It's at the center of a giant elliptical galaxy, and it has a powerful jet coming out of it that's been seen across multi-wavelength observations for decades now. Sagittarius A star is a run-of-the-mill black hole in a run-of-the-mill small spiral galaxy. It's 4 million solar masses. It's accreting much slower than M87, and it doesn't have a jet that's been observed as yet in images. So this was actually pretty peculiar for us to find out that their magnetic field structures actually turn out to be really similar, and that this may be actually a universal kind of feature of these types of black holes that we're looking at. So the next step is to really understand whether this actually means whether Sagittarius A star indeed has a jet, as the theoretical model that best fits things, as Michi just described, also predicts that there is a jet in that simulation, so there should be one in Sag A star hiding there. How do we get a jet in Sag A star, and how do we complete the story of how jets are launched from these black holes? So, we've seen now these two static images. The next step is, of course, to look into dynamics and to look into properties of the black hole that would teach us about this mechanism that launches jets. So there's a well-known mechanism that's sort of broadly agreed upon called the Blandford-Schneiek mechanism, in which the rotational energy from the black hole shears the space-time around the black hole and puts all these field lines very tightly close to the horizon, and they become strong and ordered and eventually launch a jet. So this mechanism is broadly agreed upon to be what's launching these jets in these black holes, but we're slowly building up evidence through observations that this really might be the real mechanism. So where are we going in the next few years? Of course, we keep observing with the Event Horizon Telescope. This is kind of the array in 2024. We have 3 new stations compared to 2017. We've observed several more years of M87 and Sag A star with results coming out. But in the next decade, we're thinking about going further. We want to add more telescopes, more observing frequencies. So the next generation Event Horizon Telescope project, led out here at the CFA by Shep Dolman, is an ambitious expansion project for the EHT to add up to 10 new dishes at different frequencies at strategic locations in order to pick out this faint emission in M87 and Sag A star and eventually take us into the era of black hole cinema. So we want to observe more often to create movies of black holes. In the case of M87, it would allow us to directly connect the ring around the black hole and its outward jet, where we can learn about how black holes accrete material, how electrons are accelerated, how the spin of a black hole can actually power these jets, and what are the physical conditions and mechanisms in these jets together with the black hole. The NGHT at its peak with the 10 new stations will also have sufficient instantaneous coverage to make movies of Sagittarius A star on very short timescales, where we could start to learn about the dynamics of this black hole and determine physical conditions for flares, which again tell us properties of the magnetic fields and the accretion flow. Then further out, we have another cool project. We're thinking about expanding the resolution of the EHT into space, and one of those concept missions led out here at the CFA by Michael Johnson and the Black Hole Explorer team. And the Black Hole Explorer is a mission to chase this to image this photon ring feature, and this photon ring is a sharp circular feature hidden within our EHT images that is created by light making specific orbits around the black hole and encoding properties of the space-time around the black hole. And we think that the photon ring carries information about black hole spin, and by imaging the photon ring, we could measure the spin of our 2 black holes. And in fact, this is what the EHT would see in these kinds of simulations, where we would expect a sharp photon ring. The EHT kind of washes it out because we don't have the sufficient resolution to resolve it. But with BECS, we'll be able to actually see movies of gas around the black hole and the photon ring popping out. And in fact, these beautiful reconstructions by Paul Tita show this bright photon ring feature coming out, and this is the kind of image we would expect from adding the Beck's extension to the EHT and measuring the spin of M87 and Sagittarius A* in order to link this entire story of this Blandford-Nyack process and the launching of jets and magnetic fields. So this is where we're going in the next decade. So I want to end off by showing our beautiful polarization images and get you excited about the future. And I want to invite the panel to come up again so that you can take questions. Thank you. Can we turn on this one too? Okay, perfect. I'm going to give this to you. And please raise your hand for questions. And I'll bring you a microphone. Yes.
So what limits did you place for Sag A* on inclination? Can you just repeat what a likely maximum where 90 degrees is edge on and 0 degrees is face on? But if you can give me a number, then I have a question that would follow that number.
I'm not going to, so I will say that in the GRMHD scoring, we have ruled out inclination 10 and inclination 90 degrees, which is sort of, we've ruled out the very edges of that parameter space. I'd be very hesitant to go further and say that. So we don't think it is perfectly face on, and we don't think that it's perfectly edge on, but that leaves most models intact.
The reason I was asking is the old question of the Fermi bubbles, which strongly suggests that it is closer to 90 than to 0. And so if further analysis and better data, higher resolution data converge, that'll be very interesting to put that to rest.
Yeah, so I don't think this is necessarily contradictory. In cosmological simulations, we see that even if you have a jet that is going off, say, into the plane of the disk, it's possible that it, depending on the turbulent structure of the ISM, is going to get deflected and eventually follow the path of least resistance, and then you'll see something that'll go up and down as we see the Fermi bubbles. So observing the potential jet with NGEHT is going to be important for resolving this picture.
I can say it and you can repeat it for the online audience. Congratulations, this is a fantastic work, guys, so great job. My question is also similar to this jet because it's very intriguing. If you guys had a wish list, are there other wavelengths of observations we could do? Because you just say it's a hidden jet, but it would be nice if we had other ways to maybe get information out of that. What do you guys think is maybe possible?
Right, so the question was if we have a wish list about what kind of observations would enable the jet detection. Maybe I can answer that one. So the NGHT actually at 86 gigahertz is the answer to that. We have a graduate student here, Randy Chavez, who's working on a great paper on showing that that's going to be possible. We really think that 86 gigahertz, because at that wavelength, at that frequency, the jet emission is more optically thick, so it's brighter in the image. But right now we're kind of blocked by interstellar scattering and instrument resolution and sensitivity at that frequency with what is existing. With NGHT, with the bandwidth upgrades, and with these amazingly sensitive telescopes adding 86 gigahertz receivers to them, we think they'll definitely have the ability to resolve a jet if this model that shows the jet is really what's lurking in the galactic center. We'll be able to see it.
Yeah, this is a fantastic result. So I have a question about energetics. So if you take Sag A* and M87 and you scale the magnetic fields, are those similar or they are different? And what's energetically you can tell about this?
I can answer it.
No.
Well, they're actually pretty similar in terms of absolute number and Gauss. They're both roughly in the 30 Gauss range. But what matters more is how strong the magnetic field is compared to the gas pressure in the system. And in both of these, the models that do the best are the ones where the magnetic field has saturated to this mad limit.
So a striking thing in this Sgr star image, the polarization is kind of covers 3/4 or more of the ring, but there's this little gap in the bottom left. Is it that everything is weaker there, the intensity is low, and you cannot reconstruct polarization, or is the fractional polarization itself really low there? Can you tell from the image reconstructions?
Yeah, I think it's mainly an effect of just the total intensity there being larger, and it's really difficult to say anything about a structure where we have very low intensity. There's also the uncertainty on the structure along the ring is also still pretty significant. We see some differences there between different methods. So yeah, I think it's a combination of just weaker polarization, but yeah, also don't interpret it too strictly what is happening along the ring with these different knots.
So thank you. This has been extraordinary. I'm trying to connect in my head what you said. I think you said first at the beginning about there's a lot of temporal variation in this story, and I've got a beautiful static image. So how should I relate that static image to things that change on timescales of minutes?
So the two strategies that we described, averaging before and averaging after, are both averaging. So you should imagine that this is equivalent to a time averaged image. So I think we saw Angelo show some of these movies, right? And then he showed the time average picture after to illustrate the difference in the polarization signal between the two different simulations. And that's the kind of thing that you should imagine that we're trying to reconstruct. But that's a great question. I think there's one modest addendum. One of the missions of NGHT is to take the static image and make it move. But even now, what we can say is that we have a statistical representation of how much fluctuation there is about this static image in Fourier space. And it turns out that for Stokes I, that matches up with the expectation from the GRMHT simulations, which is actually quite a nice result. For the polarization, I don't think we did that analysis for.
When we first had the image of Sgr star, it seemed that the three bright spots were probably artifactual. And my question is, having looked with such care at the polarization, do you have a further view about the status of that?
So when doing the polarization analysis, we did see again those three spots pop up. So I would say there's probably something in the data that is indicating that these are there. We see them with different methods, but also not all the time. So it's still difficult to say. But the polarization analysis did not reveal a completely different picture than what we had with the total intensity.
Any last question? Last question?
So, given the best bet models and the jets, like how bright do you expect the jets to be? At what level do you think we would expect to see them with the NGHT or future arrays?
Sara question.
Yeah.
Randy, you can tell us.
Yeah.
Randy can tell you. So I think in the simulations, the jet is quite faint still. I don't think it will look like the one in M87 at 86 gigahertz. We're still looking right now. Our images, are a dynamic range of like 10, maybe less for Sgr star. I think we'd expect the jet to be at the 100 to 200 level, right, Randy? Yeah. So that's the sensitivity the dynamic range that we need to go down to be able to pick it out. And I think based on Randy's work, I think we're pretty confident that we can get there. All right, then thank you everyone for joining this colloquium, and let's thank the team again.
We did it. Oh wait, we need to take a photo before I take that down.
It's not